This is a video for AQA Further Pure Mathematics, Vectors section 2.6, where we're looking at the perpendicular distance from a point to a line. Well, the question is concerning then a point and a line either in 2 dimensions or 3 dimensions. And we may want to find the perpendicular distance from A to L, in other words the length of a line which is at 90 degrees to the direction of L, and then the coordinates of B which are on the line. Now what I want to do first of all is to think about what steps we need to take to go through this problem. So here I've just added a few things into the diagram, the vectors from the origin to A, B, and then the position vector of some known point P on the line and the direction vector. So what we need to do first of all is to work out an equation of the line L in the usual form: r equals point P plus mu times the direction. And then, having got that equation, we use this to find an expression for AB, the vector A to B, in terms of mu. Once we've got that expression, we know that AB is perpendicular to the line, so that if we can find a value of mu such that AB dot product with the direction D is equal to 0, we know that we've got the correct point. So the dot product being 0 gives us perpendicular lines. Once we've found that value of mu, then we can find it to find the length of AB. So what I'd like you to do now is to pause the video and to try that for this particular problem here. So we've got the length that we want to find is from A to the point B, where we've got a line joining 2 points this time, so you're going to have to work out the direction vector as well. So go through those steps yourself, working from A, B, and then seeing if you can find a value of mu in the equation that you get for L, which gives you AB dot product with the direction vector equal to 0. So the first thing we need to do is to work out an equation for the line. Well, the direction vector we can get from the 2 known points there. So if we want the vector from R to P, we need to take P minus R, so the position vector of P minus the position vector of R, and we can see quite easily that that is equal to 5, 13, 3. Once we've got that as our direction of the line, then the equation of the line is the position vector of one point, let's say R, so there's R, plus mu times that direction vector. In other words, we can say that a point on the line, OB, or the vector for OB, is the vector for a point that we know, 1, 0, 2, plus mu times the direction vector 5, 13, 3. And if we write that out as one vector, then it's 1 plus 5 mu, 13 mu, and 2 plus 3 mu. Now what we want then is to find the particular value of mu such that AB dotted with the direction vector for the line D is equal to 0. Well, we can get AB, the vector from A to B, by looking at the vector for OB, the position vector of B, minus OA, the position vector of A. In other words, it's the expression that we've found above and then minus the position vector for A, so that will become negative 2 plus 5 mu, negative 1 plus 13 mu, and 3 plus 3 mu. This is the vector for AB, so we want that dotted with the vector for the direction D. So we need to take this one, negative 2 plus 5 mu, negative 1 plus 13 mu, and 3 plus 3 mu, and dot that with the direction vector for the line, which is 5, 13, 3. If you multiply that out, you get negative 10 plus 25 mu, etc. And then that gives a long expression which you can check, which comes to give us mu is equal to excuse me, 14 over 203, or 2 over 29. On the next slide I've got a nice neat version of this for you, so that if you wanted to print it off you could. Now once we've got the value of mu equal to 2 over 29, we can then use that to find AB and hence the length. So that's quite straightforward. We take the value 2 over 29 and substitute it into the expression for AB, and then that will give us a particular value, and hence we can find the length of that line by using Pythagoras' theorem. So there we are, taking our value mu 2 over 29, we get that AB is given by this expression on the second line, and therefore the perpendicular distance. In this method then we use the perpendicular idea of the dot product being equal to 0 to find the value of mu. There are alternatives however, and so I just want to consider one of those very briefly. In the same way as we did before, we can find that the vector for AB is given by this expression, negative 2 plus 5 mu, negative 1 plus 13 mu, and 3 plus 3 mu. So we could then work out an expression using Pythagoras' theorem for the square of the length of AB. If we do that, it's just squaring the values, and we can see that we get this expression 203 mu squared minus 28 mu plus 14. Now we want to find the minimum length of AD, and that of course will be the same as the minimum length of AB squared, or at least it will be the same value of mu that gives that. So because we're looking for a minimum, that sort of suggests that we could use differentiation. So if this expression here is going to be equal to a minimum value, its derivative is going to be equal to 0. So differentiating that gives 406 mu minus 28. We want that to be 0 because of the minimum, and hence mu is equal to 2 over 29. Once we've got 2 over 29, then you can either proceed in the way that we did before to find the length of AB, or substitute the expression 2 over 29 into the line above to get AB squared and then its square rooting. So AB squared substituted into the expression gives us that value, 378 over 29, and then AB is obviously then the square root of that, which again is 3.61 to 3 significant figures. Well, that concludes this video. In the next one we'll be looking at the perpendicular distance between two parallel lines.